The example I'm going to describe, the theoretical interpretations. Momentum P is conserved in all types of collisions. Whenever there is a collision, the momentum is conserved. The total momentum before collision equal to the total momentum after collision. Now the kinetic energy may or may not be conserved. If you remember, we did a problem in the last class where a truck and a car collides and the system moves together as a single body. And we found that 20% of the kinetic energy was lost. Well, kinetic energy may be conserved or may not be conserved. In most collisions that we are familiar with, kinetic energy is not conserved. Why? Because while colliding, some of the initial kinetic energy gets converted to heat energy, sound energy, and also it is used in doing work in deforming the object. And therefore, for most practical purposes, kinetic energy is not conserved in practical collisions. If no energy is lost in deforming objects, then kinetic energy will be conserved. And that happens only in the minute world where molecules collide with molecules. In the room, for example, there are millions of molecules hitting against each other at all times. And these collisions can be considered to be where kinetic energy is conserved, but not in our everyday life. So, if there is no loss in energy during collision, then kinetic energy will be conserved. Alright, watch the definition of elastic collision. A collision where momentum and energy both are conserved is called an elastic collision. So, in an elastic collision, the momentum is conserved, also the kinetic energy is conserved. That means in an elastic collision, no energy is lost in doing work in deforming the objects or producing heat or sound and so on. In gas, when gas molecules collide, it is assumed that the collisions are elastic. No energy is lost in collisions. For an elastic collision, initial momentum equal to final momentum and initial kinetic energy equal to final kinetic energy. It means momentum is conserved, kinetic energy also is conserved. If the final kinetic energy is not the same as the initial kinetic energy, then some energy is lost. Such a collision is called an inelastic collision. So distinguish between the two. In an elastic collision, no energy is lost. Whereas in an inelastic collision, some energy is lost so that the final energy is less than the initial kinetic energy. So, for an inelastic collision, momentum is conserved. Momentum is conserved in all types of collisions. But for an inelastic collision, the final kinetic energy will be less than the initial kinetic energy. Okay, let's consider an object of mass m1 moving to the right with a velocity v1i. You are familiar with these notations. There we have an object of mass m1 moving to the right with a velocity v1i. A second object of mass m2 moves to the left with a velocity v2i. What's that moving? A second object of mass m2 moves to the left with a velocity v2i. They collide and object 1 moves away with a velocity v1f So they collide. Look at that. The object 1 moves away with the velocity v1f, and velocity of the object 2 after the collision is v2f. So it collides and moves away with the velocity v2f. Okay, I want you to be familiar with these terms. v1i is the initial velocity of object 1. v2i is the initial velocity of object 2. They move towards each other, collide and move away. Object 1 moves away with a velocity v1f, final velocity of object 1. And object 2 moves away with a final velocity v2f. Okay? The momentum of the object 1 before collision. What is the momentum of this object before collision? m1 v1i. And the momentum of the object 2 before collision will be m2 v2i. Therefore, the total momentum before collision will be pi. Pi is the total momentum before collision, is m1 v1i plus m2 v2i. Alright, what is the total momentum after collision? The momentum of object 1 after collision is m1 v1f. Momentum of the second object after collision is m2 v2f. So the total momentum after collision, pf, is m1 v1f plus m2 v2f. And you know that for all collisions, momentum is conserved. That means pi equal to pf. Let's write that. pi equal to pf means m1 v1i plus m2 v2i equal to m1 v1f plus m2 v2f. Let's rearrange it. I'm going to move the term in m1 to the left and the terms in m2 to the right. So if I move m1 v1f to the left and factor out m1, I will get m1 times v1i minus v1f equal to m2 times v2f minus v2i. I hope you followed that. But all I did is moved m1 v1f to the left, factor out m1 from there, move m2 v2i to the right, and factor out m2 from there. Now, this is the equation that we obtained by considering the conservation of momentum. This is the conservation of momentum equation. Let's now consider the kinetic energy. What is the initial kinetic energy of the two objects? The initial kinetic energy of the first object is 1/2 m1 v1 I squared. Kinetic energy of the second object before collision is 1/2 m2 v2 I squared. So the total kinetic energy before collision is 1/2 m1 v1 I squared plus 1/2 m2 v2 I squared. What is the total kinetic energy after collision? It will be 1/2 m1 v1 f squared plus 1/2 m2 v2 f squared. If the collision is elastic, then Ki will be equal to Kf. So let's take the case of an elastic collision. For an elastic collision, Ki equal to Kf. It means 1/2 m1 v1 I squared plus 1/2 m2 v2 I squared equal to 1/2 m1 v1 f squared plus 1/2 m2 v2 f squared. Well, it looks long, but it is a very simple equation. Let's take this equation to the next slide. There you are. Now, what I'm going to do, first of all, 1/2 exists in every term. I can cancel it. 1/2 will cancel everywhere. And just like I did in the previous case, take the term m1 v1f squared to the left and m2 v2i squared to the right, and factor out m1 on the left and factor out m2 on the right. So what does that give you? m1 times v1i squared minus v1f squared equal to m2 times v2f squared minus v2i squared. Well, to simplify this, we are going to use the simple algebraic factoring, that is a squared minus b squared. I'm sure everybody knows how to factor that. A squared minus b squared is a minus b times a plus b. You see? v1i squared minus v1f squared is v1i minus v1f times v1i plus v1f. Is that right? Factoring difference of two squares. Similarly, factoring difference of two squares here, v2f squared minus v2i squared is v2f minus v2i times v2f plus v2i. Now, if you noticed, if you can watch this in color, well, the colors don't record very well. But if you look at our first equation, what is it? m1 times v1i minus v1f equal to m2 times v2f minus v2i. So this quantity on the left side, m1 times v1i minus v1f, is the same as this quantity on the right side, m2 times v2f minus v2i. That means they can be cancelled. They are the same. Now that leaves us with the simple equation. We have v1i plus v1f equal to v2f plus v2i. Alright? And I'm going to rearrange it. Look at the way I'm going to rearrange it. It is v2f minus v1f. Do you see that? v2f minus v1f equal to, take this to the left. Let me do that for you. Now, it's going to look like this. We have v1i minus v2i equal to v2f minus v1f. Now, on the left, I'm going to factor out a negative sign. That will become negative of v2i minus v1i equal to v2f minus v1f. You see one more time? Take this v2i to the left side, we get v1i minus v2i equal to v2f minus v1f. And then here I factored out a negative sign. You see, negative of v2i minus v1i equal to v2f minus v1f. Alright, that's what this is. Now, what does that actually mean? What is the meaning of v2f minus v1f? And what is v2i minus v1i? Well, let me see if we can have a look at this. Now, here I have the first object of mass m1 moving with the velocity v1i, and the second object of mass m2 moving with the velocity v2i. Now, what does v2i minus v1i represent? Look at that. v2i minus v1i is the velocity of approach. The v2i minus v1i is the velocity of approach. And what does v2f minus v1f represent? v2f minus v1f is